Greetings. I hope everybody's doing well, and welcome to class. So this is how we will conduct class for now. Hopefully it works well. If you have any issues or questions with it, please let me know, or any feedback in general. So please feel free to email me, and we can figure out a time to discuss any questions or concerns that you might have. So what we're going to do is I'm going to run through some material. I'll try to make these videos short, and then I'll ask you to do some questions from a worksheet. You can access those questions on my website. You can either print off the worksheet if you have a printer, otherwise you can just do it right on notebook paper. Just please remember to label that notebook paper 8.1 and what numbers you're doing so that I can see the work that you're doing and also the answers, and that when we do come back to school, at whatever point I can check that and we can move forward from there. So this unit is on gas laws. So we're going to start here. So just give me a second. These videos will become hopefully more smooth and better as time goes on. But for now, we're going to learn as we go. So today's learning objectives are: I want you to leave here being able to define what pressure is, being able to convert between the units of pressure, and being able to define what STP is. STP is something that we've talked about before. I'm just going kind of to review what it is. But if you remember it, great. If you don't, today we're going to take a chance and review it. So this unit, like I said, is on gases. So what I'd like you to do first is either jot this down or think in your head. We've done this before as well. How do gases differ from liquids and solids if I'm thinking of them at the molecular level? Remember, we're thinking down to molecules now, okay? So we're not just like imagining gases, because you might say, well, I don't imagine anything. I'm in a room full of gases right now. But what would it look like if we were able to view them at the atomic level? And how does that differ from viewing a substance that's a liquid and viewing a substance that's a solid? Okay. So hopefully you're imagining or drawing this. So if I look here, these gases, the particles themselves are completely spread out. They're taking up whatever space the container allows. Liquids are closer together. They fill up from the bottom to the top. Okay, they're affected by gravity, and solids have their own shape. Here's a solid right here. Solids have their own shape. Okay, the particles are much closer together. So what we're focusing on this unit is gases. Okay, so we're focusing on this right here. And how do gases change when I change variables like temperature and pressure and volume? Okay, but today we're just going to focus on pressure. All right, so I'm going to skip ahead, but I will kind of occasionally post videos that are cool. This one's from Jimmy Fallon, where he had a guest talk about gases and show some cool experiments on gases. And you can find access to these videos on my website as well. All right, so first things first, let's look at our periodic table. So on our periodic table, I have a list of elements, okay, and we're very familiar with this periodic table. Okay. If I highlight the elements that are gases at room temperature, or excuse me, at STP, it would look like this. And what I want you to think about is, what do all of these elements have in common? Hopefully you're thinking all of these elements are nonmetals. Okay. So nonmetals must become gases more easily than metals. Well, what type of compounds do metals form? Ionic? Covalent? That's what we're going to talk about next. But first, let's quickly remind ourselves what STP is, because what this chart is it's a chart highlighting the elements that exist as gases at STP. And remember, STP is 0 degrees Celsius and 1 atmosphere of pressure. Okay, so that's just a temperature, a specific temperature and a specific pressure, where we do a lot of science experiments, especially those that involve gases. Okay, so what I see on this periodic table is all of my elements that are gases at STP. okay? The other substances, solids or liquids. All right, so like I said, all of these substances that we're seeing here are nonmetals. So nonmetals form what type of compounds? Because what I want you to recognize is what types of forces are involved in gases typically. Okay, what type of forces are involved in gases typically? And that should hopefully allow us to understand what type of compound is more likely to be a gas. Okay, so let's first refresh our memory on those two terms that I always want you to remember, ionic and covalent. And ionic, remember, are metals and nonmetals. Now, if I look at a list of ionic compounds, I'm going to notice there tend to be solids at room temperature. Now, why? Why are these solids at room temperature, but nonmetals by themselves are gases at room temperature, or tend to more likely be gases at room temperature? Okay? Well, it's because of that attractive force. Okay? And hopefully, if I say the word lattice, you're like, oh, I know what that is. Lattice is the shape that all of these ionic compounds have, because the positives are attracted to the negatives, which are attracted to the positives, which are attracted to the negatives. And that force of attraction is very strong and is going to hold all of these ionic compounds together very tightly. And remember, if the molecules are held together very tightly, they're more likely to be what? A solid, a liquid, or a gas. Hopefully you're thinking solid. Okay? These particles are more likely to be a solid if they have a stronger force of attraction. And that electrostatic force is a strong force of attraction. But what about covalent? Covalent has those weaker forces of attraction. Okay? Much weaker than these electrostatic forces of attractions in ionic compounds. So because they have a weaker force of attraction between molecules, okay, much easier to separate, break apart, okay, it's a lot easier for them to be gases. And some of them might already be gases at that specific temperature and pressure that we call STP. So the majority of liquids or solids covalent compounds are typically liquids or solids at STP, but they are a lot more likely and a lot more easily become gases. Why? Why do covalent compounds tend to become gases more easily than ionic compounds? Hopefully, you're thinking the forces of attraction are weaker. The forces of attraction are weaker and allow those particles to separate more. So what I would say to answer this question is intermolecular forces are much weaker in covalent compounds than the electrostatic force of attraction in ionic compounds. That makes covalent compounds gases more easily than ionic compounds would be. Okay. All right. So what I have here is just a list of covalent compounds, or a list of substances found as gases at room temperature. And if I look at this list, I'm going to look, do I even see any metals on this list? No. They're all nonmetals because they're held together by weaker forces of attraction. Covalent compounds are held together by weaker forces of attraction called intermolecular forces. Remember, hydrogen bonding, dipole-dipole, or London dispersion. Those weaker intermolecular forces make these things gases. Okay? So how would I describe gases? Because I also not only want to identify what substances are likely to be gases, but I want to be able to describe gases. So take a second, you can even pause the video, and think about how would you describe a gas. Okay, and I'm going to move right ahead. All right, so 4 physical characteristics of gases that we should be comfortable with. Okay, gases. Gases assume the volume and shape of the container that they're in. The gases in this room right now take up the entire space of this container. I'm not going to all of a sudden walk over to my front door and run out of air, okay, because there's no gas there. The oxygen, the air in this room is spread out completely, okay? Gases are the most compressible state of matter. What does compressible mean? Hopefully you're thinking pushed together. So if particles are farther apart, they're more easily able to push together. which should make sense. Gases. Mix evenly and completely when confined to the same container. If you open up something that smells bad or smells good, okay, over time everybody in the room is going to smell it. Or if you're cooking something, okay, those odors given off spread throughout the room, the container that they're in. They spread out evenly. Okay, and we're going to study that term diffusion, which is the spreading of gases as this unit goes on. And the last one, gases have much lower densities than liquids and solids. Density, or again, mass over volume. So they're more, or excuse me, less dense than a solid because they're farther apart. Okay, so when I'm comparing gases to liquids and solids, which I am right here, notice the gases are farther apart. And all of these physical characteristics describe those gases. All right? But what about pressure? Okay, what about pressure? That is our goal today, is to be able to define pressure and be able to convert between units of pressure. So what is pressure? Maybe you're under a lot of pressure right now trying to get all your work in before the end of the quarter. Okay? Or you have a lot of work to do at home. Okay? A lot of people are under a lot of pressure now to stay home. What does that mean? Okay? What we're trying to do here when I'm trying to apply pressure is I'm hopefully applying force. So gases exert pressure on any surface that they're in. Why? Because what are they doing there? They're applying force to it. Are gases running around in this perfect order? No, they're flying all over. It's chaotic, okay? They're flying around and applying a force to a specific area. Okay? And this force can be seen when we look at a straw. So let's look at a straw and describe what's happening here. Okay, so if I have a straw, right here, there's air particles in that straw and there's air particles out of that straw. So what happens when I breathe in is I remove these particles in the straw and they go up. Okay, so once these particles are removed in the straw, the pressure goes down in that straw. There's less air in there. But I still have air pressure on the outside of the straw. So what does that do? This pressure on the outside pushes that liquid up. So we're not really sucking the liquid up when we're using a straw. The air outside us is pushing that liquid up because of that difference in pressure. No pressure in here, pressure out here. That's where I see that difference. And that's what happens when you blow up a balloon. Okay, if I breathe into a balloon and it increases in size, it's because those particles are applying a pressure to the outside. But what is pressure? How are we going to define pressure? Pressure is a force applied to an area. So these gas particles right here are moving around, applying force to the outside of this container, or this balloon right here. There's pressure on the inside and the outside. And the size of this balloon is simply controlled by a balance of pressure on the inside and the outside. If I add more particles or heat it up, or I do things to change the pressure on the inside, it's going to change the size. Or if I do things to the outside, it's going to change the pressure and change the size of this balloon. And that's what we're going to be studying this unit. So I want you to be able to first define pressure, and then we're going to change pressure and see how that affects other variables. Okay, so again, let's define pressure. So a textbook would define pressure as a force applied to an area. So if I apply a force to something, okay, these two particles run into each other. Okay, they are applying a force to each other. Whatever area they're applying that force to allows me to define pressure. And I can measure pressure with different units. Okay, different units. Just like I can measure distance in different units. I can measure it in centimeters, I can measure it in inches, I can measure it in feet. I can do the same thing with pressure. So there's going to be a ton of different units you use to measure pressure. Could be atmospheres, millimeters, mercury, torrs, depending on what you're using. Okay, if you're looking at your tire pressure, it might be in pounds per square inch, or if you're measuring weather, it might be in millimeters mercury. Okay, so the unit of pressure is going to vary depending on what instrument you're using. All right, but this is the instrument first used to measure pressure. It was invented I think by a guy named Torricelli, and I might talk about that in a little bit, but it's a barometer. So what it measures is I have this empty straw here. It measures how strong, how much pressure there is on the outside to push up this mercury on the inside. And if it gets pushed up farther, it's more pressure. There's more force here. Okay, so the force of air particles out here pushes that liquid up the straw. Okay. We're going to focus on a common unit of pressure, the ATM, because that's going to be one of the more common units that we discuss in this unit. So, atmospheric pressure. This is the pressure exerted by Earth's atmosphere. And this depends on a lot of things. It depends on temperature, it depends on location, it depends on weather condition, it controls weather conditions. Okay, so this is how they predict weather patterns. And as you travel up, like in an airplane, okay, in an elevator, if you're climbing to the top of a mountain, you're going to notice a difference in pressure, and your ears are going to pop. And we'll talk about that a little later on. But why? Gravity. Okay, as I go up, there's less force pulling down, so therefore the particles spread out more. So as I'm going up, there's less pressure due to that force of gravity. Okay, so what I want to do today and how I want to end this class is just converting between units of pressure. Okay, so pressure, this is what I talked about earlier, was first measured by a guy named Torricelli in the 17th century. He invented that device called a barometer, which measures pressure. Okay, so we're measuring pressure by how far it moves up in essentially a straw. And they use mercury because it's more dense than water. If you made a barometer out of water, it'd have to be really tall to account for the less density of water compared to mercury. All right, so this is an early barometer. It looks just like this. So over here, I'm going to move me over here. Okay, over here, I have mercury, and it's being pushed up in this evacuated straw. And the farther it gets pushed up, the greater the pressure. Okay, so if I have a greater pressure outside, that mercury might move this liquid up higher. If it moves up 760 millimeters, that's my unit of pressure. So they've decided that 760 millimeters is the pressure at sea level. At sea level, I can also call that 1 atmosphere, because above you, you have 1 atmosphere. If I go below sea level, I have more than 1 atmosphere above me. If I go up high, I have less than an atmosphere above me. So this is a unit of pressure. Now, all of these units are measuring the same thing. Just like converting inches to millimeters or centimeters, I'm going to do the same thing. And I want us to get comfortable with these units of pressure first so that we can convert between units. So that's going to be what we do first. So we're going to convert between these units of pressure. And that's going to be today's lesson. All right, so on worksheet 8.1, which you can access on my website, there's a few problems. I'm going to do a few examples here, and then your job is going to be to do a few more and get comfortable with converting these units of pressure. All right, so first, the example. I'm going from 5 atmospheres to kilopascals. From 5 atmospheres to kilopascals. It's doing the same thing that I've been doing, like going from moles to grams, or from hours to minutes. We're using dimensional analysis to convert between units. So I'm going from atmospheres to kilopascals. Okay? So I'm starting here with 5 atmospheres. That's my starting point. That's the number I'm given. The unit that I'm coming from goes on bottom. The unit that I'm going to goes on top. Well, what are my conversion factors? Like, I know there's 60 minutes in an hour. So if I'm converting from minutes to hours, minutes is going to go on bottom, 60 minutes, 1 hour would go on top. But I don't know my units of pressure. Well, that's what I give you on this worksheet. 1 atmosphere equals 760 millimeters of mercury, which equals 760 torrs, which equals 101.3 kilopascals and equals 14.7 psis. I like to draw a line between each of these because I don't want you to be confused, and like some students look at this as like millimeters of mercury equals 760 or torrs equals 101.3. It's 1 atmosphere equals 760 millimeters of mercury equals 760 torrs equals this. These are all equal to one another, just like 60 minutes, okay, equals an hour. Okay, 60 minutes equals an hour. All right, and I'm doing the best I can with writing here, but hopefully you see the point. These are conversion factors used to convert between different units. Okay? All right, so I'm going from ATMs. Where's ATMs? Right here. I'm going to kilopascals. So the unit that I'm coming from goes on bottom. What is the number that coincides with that? 1. The unit that I'm going to goes on top, kilopascals. What is the number that coincides with that? 101.3. So here, would I multiply, divide? Do I do both? What do I do? Hopefully you're thinking it's on top. I multiply. Please label everything. Keep with your units, show your units, because again, as these get longer, as these get more complicated, okay, it's easy to make mistakes on units. So please label everything. And then that equals 507 kilopascals after multiplying. So we're going to do just a couple more examples. Here's example number 2. I'm going from 500 torrs to atmospheres. So I find torrs right here, and I'm going to atmospheres. So I start with 500 out front. Torrs goes on bottom, 760. I'm going to atmospheres. 1 atmosphere goes on top. So would I multiply or divide? Hopefully you say divide. And you get 0.658. Number 1, 359 millimeters of mercury. Now on the sheet, it looks like this. So if you printed it off, it looks like this. How I want you to set this up, this number goes out front. And then where I'm coming from, millimeters of mercury would go on bottom. How many? 760. What I'm going to, atmospheres, would go on top. How many? 1. These two are equal to one another. So what would I do here? Multiply or divide? Hopefully, divide. And you get an answer of 0.472. I started with 3 sig figs. I ended with 3 sig figs. One more example to wrap things up. I'm going from 992 millimeters of mercury. That's going to go out front. I'm going from millimeters of mercury to kilopascals. So to find my conversion factor, I can highlight it up here. Here's 760. That's going to go on bottom. Kilopascals is going to go on top. But here I don't have a 1. So what do? I need to multiply and divide. So there's my setup. I take 992 times 101.3 divided by 760, and I get an answer of 132 kilopascals. All right, so hopefully this is a good introduction as to what we're going to be studying this unit and getting comfortable with converting units of pressure. Okay, we're going to start gas laws in the next lesson, but for now, I would like you to just focus on doing numbers 1 through 10 on 8.1. And again, you can do this on, if you print it off, or on a piece of notebook paper would be fine. Just label it 8.1 and do numbers 1 through 10, showing your work, remembering units for everything. All right, so hopefully that was a good introduction. Hopefully this goes well. Please let me know if you have any questions, any issues, anything like that. But this is the beginning of 8.1. So, see you soon.